Okay, before you even get into this video, what I want you to do is pause and make a prediction. How do you think this reaction is going to start? If I am reacting this alkene over here on the left with the hydronium ion here. And one thing I'm going to tell you before you dive in is that the hydronium ion is really a catalyst. Uh, so we also are going to have water present. Um, we'll have lots of water with just a little bit of this hydronium ion present as a catalyst. What I want you to do is make a prediction and draw what you think that reaction mechanism would look like. You could be entirely wrong, and that's okay because I'll walk through it afterwards. But I want you to practice that skill of using your understanding of organic chemistry to make a prediction. So pause now, and after you've worked at it for 5 minutes or so, come back and restart. Okay, hopefully you identified that we have an acid here, a strong acid, the H3O plus. And just like the reactions where we had HBr or HCl, that kind of strong acid reacting with an alkene, you might predict that your first step would be for pi CC of the alkene to attack hydrogen. In this case, that's going to release water. We have a choice of making a primary or a tertiary carbocation. We're going to choose to make the tertiary carbocation. And now we've made our high energy intermediate. We know that a carbocation will bond to the first nucleophile it sees. So I need to think about, well, who's around that has a lone pair that might be able to share that lone pair with this carbocation? And the answer is, in this case, water is the first nucleophile that the carbocation is going to see. Water has a lone pair, so water can share its lone pair with the carbocation. That will give me this intermediate, which still has a charge. But I did tell you to start that H3O plus was a catalyst here. All right. So I'm not entirely done with my reaction. To get to the final product of my reaction, I need to make a neutral product. And the way I'm going to get there is in the first step, H3O plus was used. I'm going to do a step now that regenerates H3O plus. Anytime you have a catalyst in a reaction, it will speed up the reaction without getting used up. And since water in this case, since H3O plus was a catalyst, it can't get used up. So I need to regenerate it in this last step. And the way I'm going to do that is to come and deprotonate to make this product and regenerate my H3O plus. Okay. So maybe you were able to make a prediction of the first step. Maybe you were able to make a prediction of the second step. That last step, not something that you've seen before, so you might not have predicted it. But it is something that we're going to see pretty commonly. In reactions, we often have very acidic hydrogens as intermediates toward the end of the reaction. And I know that the pKa of this hydrogen here is about -2. If you refer to your pKa list, it's an oxygen with a positive charge, sp3 hybridized, bonded to a hydrogen. pK of that is usually going to be in the neighborhood of -2. That means it's very acidic. We will sometimes use a shorthand. Um, this isn't necessarily commonly used. If you take organic chemistry at various places around the country, they may not use this notation. And of course, I always use this notation. So as a shorthand for deprotonating strongly acidic H pluses, I'll use just SOL with a lone pair, short for solvent, meaning a very acidic proton can be pulled off by any old solvent molecule or anything that's in the solution that is even weakly basic. So that last step, I might have, instead of using water to deprotonate, I might have just used Sol as my deprotonator. All right. The key here is I'm only going to use that when it's a very acidic proton, and it doesn't really matter who is coming along to deprotonate it. I just know that that H plus is being returned to the solution in some way. So only I'll only use that when I have very strongly acidic um, protons that I'm going to deprotonate. But you will see me use that shorthand a lot. So that last step, instead of H2O, I could have used Sol. It's always acceptable to use a molecule of the actual solvent. But when you look through materials, you will sometimes see this abbreviation. All right. So this is described as acid catalyzed addition of water to an alkene. How would we write it? We would generally write it this way. We have our alkene. We're reacting with H2O. We have an H plus catalyst. And we're making our alcohol. If we wanted to write this, we could also say alkene with H3O plus makes an alcohol. There are a number of different ways we could have written the thing over the arrow. H2O, H plus catalyst, H3O plus. Those are both acceptable. Now this question of what is meant by acid catalyzed. So I said a catalyst is something that speeds up a reaction without getting used up. Catalysts generally lower the activation energy of the reaction. Speeding it up without getting used up in the reaction. Now, this reaction is acid catalyzed because it turns out if you put an alkene in water without an acid catalyst, they will just sit there and look at each other. So if I just took this alkene and I added water and no catalyst, we'd observe no reaction because the reaction would be too slow to observe without the catalyst. Let's think about why that's the case. The first step of this reaction involves pi Cc donating to sigma star OH. Now, PiCC is an okay donor, but it's not very high energy. And so, in order to entice PiCC to react, you need a very, very good acceptor. And it turns out when you have the sigma star OH in a water molecule, it's not low enough energy to act as the acceptor in this reaction. That step is just too slow. But because in H3O plus now we have a positive charge on the oxygen, that lowers the energy of sigma star OH. And that's what really allows this first reaction to occur at an observable rate. So this is a reaction where the H plus catalyst really speeds up the reaction. And you really can't run this reaction without that catalyst. So here we have our second example of an alkene addition, where what we have added to the alkene was an H on one carbon and an OH on another, right? If we consider this we really added an H to one carbon and then OH to the other carbon. So that's why this is called acid catalyzed addition of water. We're adding water. We're adding H and OH, which is the same as adding water across the double bond. We can ask ourselves, did this follow Markovnikov's trend or Markovnikov's rule? Well, remember that Markovnikov's rule said that when adding a polar reagent to an alkene, the partial positive side bonds to the less substituted carbon. So the partial positive side was hydrogen. That went to the less substituted carbon. And the more electronegative atom, or the partial negative atom, bonded to the more substituted carbon. So yes, this follows Markovnikov's rule. All right, so there's your second reaction, acid catalyzed addition of water to an alkene. One theme that you're going to see going forward is a lot of reactions that can occur with water. We can run an analogous reaction with an alcohol. So what if I, instead of adding water to an alkene, I tried adding an alcohol instead? So in the second case here, I have an alkene, I have an alcohol, and I have an acid catalyst. Think about how this might result in something different. And you're going to need to think back to module 15 on carbocations to think about, given this starting alkene, what else might take place in this reaction. So again, I want you to pause and give this a try. This one I really think you could, if you've been paying attention to everything, follow through, draw the full mechanism, and predict the product. So I want you to pause, take a minute to, or take about 5 minutes to go ahead and draw what you think the mechanism looks like and predict the product here, and then come back. Okay, now that you've had some time, let's think about how this reaction could proceed. I'm using an H plus catalyst again. And notice in this case, I haven't drawn it bonded to the solvent. In reality, the H plus catalyst in this case, you would have your CH3OH, and then your H plus catalyst would be bonded to that. So it would look like this. But as a shorthand, since we're just using H plus, my first step is going to be for this to go attack the H plus. It could also be for my alkene. Alternatively, I could draw that first step as my alkene going to attack the H plus bonded to methanol. Either way is going to be okay. So in that first step, I have a choice between a primary or a secondary carbocation. I'm going to choose secondary because that's more substituted. That'll be a less unstable carbocation. And you might have at that point decided, okay, I'm going to react that carbocation with the closest nucleophile, which in this case is methanol. But you also might have, thinking back to module 15, notice that we have a secondary carbocation next to a quaternary carbon. This is quaternary. This is a secondary carbocation. So when we have this situation, you might remember that what we're going to see is an alkyl shift, where my methyl group will slide over, right? So this leads to an alkyl shift. When my methyl group slides over, that's now going to give me a new carbocation. I'm going to number my carbons to keep track of them. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4. 5 is still over here bonded to 2, but now 6 is bonded to 3. And we've taken electrons away from carbon 2. So now I have the tertiary carbocation on carbon 2. Remember, that's an intramolecular reaction, so that generally is going to happen faster than the reaction with the surrounding nucleophile. So in this case, the only nucleophile I have around would be my methanol. So at this point, I'm going to allow the methanol to come in bond with my carbocation. And that'll give me an intermediate that looks like this. Now this seems like we're getting close to a product, but I still have that very acidic proton. Well, I remember now that the acid was a catalyst, so my last step is going to involve having the solvent come and pull off that very acidic proton. That regenerates the acid catalyst, and that will yield my result here. So if you were able to make that prediction, come up with that product yourself, you are doing great. If you didn't, that's okay, right? This is hard stuff, and you've got to practice it and see it multiple times before it sinks in. So if I want to summarize what we did here, we reacted an alkene with an alcohol and an acid catalyst. And if I had to characterize this product, in the product I have oxygen bonded to 2 carbons. So this is an ether. So my product was an ether. All right, so these reactions that we've seen, these addition reactions, they have in common, all the reactions we've seen go through a carbocation intermediate. That we form a carbocation and then we attack that carbocation with the closest nucleophile. If I was reacting with HBr, the closest nucleophile was Br minus. If I was reacting with water, the closest nucleophile was water. When I was reacting with an alcohol, the closest nucleophile was the alcohol. And we get different results each time. You'll see this theme, like I said, a lot of times a reaction that we can do with water, we can do an analogous one with an alcohol. We just get a somewhat different result. The last thing that I want to talk about. So I've introduced 3 different reactions that all go through carbocation intermediates. The last thing I want to talk about is what's the stereochemical result. So if you're someone who skipped over module 8, this part isn't necessarily going to make as much sense to you, but I'd encourage you to stick with it because it is useful to understanding these reactions and how we know that the reactions follow the mechanisms that we predict. So if we were adding HBr to the alkene I've shown over here, there are a couple of different products we might predict. We could add the hydrogen and the bromine both coming out of the page or both going into the page. In other words, where the H and the Br are on the same side, they add to the same face of that alkene. Or we could imagine adding them to opposite sides, H and Br adding to opposite sides, where one is coming forward and one is going back. See here, forward and back, opposite sides, versus forward and forward, same side. We give those 2 possible outcomes different names. One we call syn addition, the other one we call anti-addition. We're going to use these descriptions in general as we look at more alkene additions, so it's worthwhile to know them. So let's think about, in our mechanism, based on our mechanism, would we predict mostly syn, mostly anti, a mixture of both? Well, in our first step in this mechanism, we know we had the alkene attacking the H of HBr. And it's really critical that you don't take an attitude here of, oh, I know this reaction, I've seen it before, so I don't need to write out the mechanism. You need to practice these mechanisms over and over. That's the way that they really become internalized. If you just think, I've seen it once, I don't need to draw it again, you're fooling yourself. You're never going to really internalize the information. So the result of that first step is that I've added hydrogen to one carbon. And in this case, the alkene's symmetric, so it doesn't matter which carbon I choose. Let's say I choose the top one. I've added a hydrogen here. And at the bottom, I've left a carbocation. Now I've got to make a choice. I have this carbon up here that I'll mark in red is now a stereocenter. It's bonded to 4 different groups. So I've got to make a choice. Did the hydrogen add from in front of the page, making that a wedge, or did it add from behind the page, making it a dash? Again, this is an arbitrary choice. So I'm going to choose to make the hydrogen come from the top of the page. That would push the methyl group back into the page. Okay, I could just have easily chosen the reverse. I could just as easily have chosen to make the hydrogen go into the page and the methyl group come out of the page. Either one of those is equally likely. The question is now, when I add the next group, when I add the bromine, is it more likely to add to the same side, more likely to add to the opposite side, or does it not matter? Well, let's think about the geometry of the carbocation for a minute. If I imagine this carbocation, I'm going to redraw this molecule so that my 2 carbons from the alkene are down at the bottom here. And I'm going to have the ring go back into the page. So for my carbon, I have hydrogen going up, and I have methyl group going down. But on my other carbon, I've got a carbocation, and that's got an empty p orbital. So I've changed my perspective here. So I've shifted so that the six-membered ring is in the plane of the page, and I've pushed the ring behind so I can just focus on these two carbons. Now, I have a carbocation, which is planar. And the thing about a planar carbocation is both sides of that carbocation are essentially equally open to attack. My nucleophile, my Br minus in this case, it could attack the top face, or it could attack the bottom face. And the thing about that is either approach is equally likely. There's nothing really blocking it from either side. And since there's nothing blocking it from either side, I would expect to get similar amounts of my two products. So I could have a product where bromine attacks from above and ends up here. Oh, I accidentally drew a hydrogen here when that was a methyl group. I apologize for that. I'm just going to draw the ring as like a dotted line here. So if bromine attacks from the above, then my bromine and my hydrogen end up on the same side. But if my bromine attacks from below, I'll end up with the bromine and the hydrogen on opposite sides. And either one of those is equally likely. In other words, I should get syn and anti. So in this case, neither syn nor anti is preferred. This will produce a mixture of both. And it turns out that when we run this reaction and we examine the products, we do get a mixture of syn and anti addition. That helps support our hypothesized mechanism that we're going through a carbocation. It's at least consistent with that mechanism. And when we're evaluating mechanisms, we're looking to gather evidence. And if we find all the evidence is consistent with it, then we tend to stick with that mechanism as being the most likely option. If we find evidence that's inconsistent with our mechanism, then we tell ourselves, okay, we need to come up with something different. You will see an example of that in Module 17, where the stereochemistry is helping us understand the mechanism for another reaction. That's going to close out Module 16. So you learned 3 different reactions, all going through carbocation intermediates. They are all going to follow Markovnikov's rule, and they are all going to result in a mixture of syn and anti-addition like we saw here, because they all go through that carbocation intermediate. Thanks.